Hello everyone, today we will continue the topic in drainage design. In this lecture, we will try to finish all the contents in drainage materials. In the last lecture, we introduced the aggregates as the drainage layer to remove the water from the pavement structure. There are actually two other materials, geotextile, which is applied to prevent the potential clogging for the drainage layer. The other one is the pipes. We will use the perforated, slotted, or open-jointed pipes to remove the water from the pavement. First, the geotextile is usually made from some strong, tough, and rot-proof polymetric fiber, and it could be woven or non-woven fabric. Usually in the drainage system, the geotextile is applied to retain soil and remove water freely from the pavement structure. It should also have sufficient opening areas to prevent the potential clogging to the drainage layer. Similar to aggregates, there is one filter criterion applied for geotextile selection in drainage design. Actually, for geotextile, the most important dimension is apparent opening size, AOS. This one is determined as the size of the glass beads with 5% passing through the geotextile. Usually, the geotextile is applied to achieve the purpose of retaining soil and preventing clogging. However, the requirements about the OS for these two functions are conflict with each other. In order to achieve the maximum retention of soil, the smallest opening size should be applied, which means we want to use the largest AOS. While to minimize the clogging of fabrics, we have to use the maximum opening size, which means we need to consider the lowest AOS. With these two requirements, we can identify the upper and lower bounds of AOS for the selection of geotextile. In order to retain soil, the geotextile should satisfy the retention criterion. For fine-grained soil with more than 50% passing number 200 sieve, the AOS requirements for woven and non-woven geotextile are different. For woven geotextile, AOS should be less than D85. Here, D85 is the grain size with 85% passing. And for non-woven geotextile, AOS is less than 1.8 times D85. In addition, AOS should satisfy additional condition. AOS should be higher than number 50 sieve, which means the opening area should be smaller than 0.297 millimeters. While for granular materials with less than 50% passing number 200 sieve, AOS should be less than B times D85. Here B is a constant coefficient, and B equal to 1 when Cu is less than 2 or higher than 8, and B equal to 0.5 times Cu when Cu is between 2 and 4, and B equal to 8 divided by Cu when Cu is between 4 and 8. And here Cu is defined as the coefficient of the uniformity, which is D60 over D10. That represents the grain size at the two different percentage. Moreover, if the soil contains particles from 1 inch to those passing number 200 sieve, then we will only consider the portion passing through number 2 sieve. And for all the other portion which will have the particles with a size higher than the number 2 sieve should be removed. Besides the retention criterion, we also need to think about the permeability criterion for geotextile. The criterion is very simple. In general, we need to think about the effective size of the fabric. For the design, we need to think about the effective size of the fabric is higher than the effective size of the soil. In that sense, we can make sure that the water flow from the soil can move freely from the geotextile. The third criterion is the clogging criterion. There are actually two different criterions applied for woven and non-woven geotextiles. For woven geotextile, we want the portion of the open area is larger than 4%, while for the non-woven geotextile, the porosity should be larger than 30%. Now let's take a look at one example to see how we can determine the range of AOS. In this figure, we have the grain size distribution of two different soils, fine-grained soil and granular material. It wants us to determine the required AOS of the woven fabric to retain the soil. So first, for the woven fabric, we will have the requirement of AOS as AOS is less than D85. This is only applied for woven fabric. And now we can check the fine grained material. Here we need to determine the grain size at 85% passing. Then going to the grain size distribution, we can get the 85% passing with the size of it's almost 0.24 millimeter, which is equivalent to number 70 sieve. Here we can get AOS is less than 0.24 millimeter for the fine-grained soil. And then we can go to check the AOS requirement for the granular materials in this figure. From the definition of the retention criterion for granular materials, we see that we don't need to think about the portion of the material which cannot passing through number 2 sieve. So we will only keep the part which can passing through the number 2 sieve and adjust the grain size distribution to the dashed line here. And with the retention criteria, we know that AOS for the granular material should be less than B times D85. And this is only applied for granular materials. From the figure, we can see that the grain size at 85% is around 2.4 millimeter. So we have D85 equal to 2.4 millimeter. And then for the constant B here, B is actually determined by the coefficient of uniformity, capital CU, and CU is D60 over D10. From the grain size distribution, we can find the D60 as 0.78, and for D10, it's a 0.042. So we get the value as 0.78 over 0.042 equal to 18.6. We find that CU is higher than 8, which can give us the value of B as 1. So with that, we can determine the range of AOS as AOS is less than B times D85. That is 1 times 2.4. It is just 2.4 millimeter. So that's the way for us to determine the AOS for both fine and granular materials. In reality, there are several ways for us to use the geotextile in the drainage system. We can apply the geotextile for the edge drain. The figure in this page shows the implementation of the geotextile in the edge drain and compared with the original edge drain. Here you can see that we can use the geotextile to cover all the filters in the edge drain. In that sense, we are able to prevent the potential clogging to the filter and also to the pipe. In addition, the geotextile can also be applied for subbase and base strand, which will try to connect the edge joints with the subbase and base respectively. The third material applied for the drainage system is pipes, which is applied to remove the water from the pavement structure. Usually the pipes are made of concrete, clay, bituminized fiber, metal, plastics with smooth or corrugated surfaces. For the underdrain system, we usually apply perforated, slotted, or open joint pipes for the drainage system. And these pipes are surrounded by some suitable aggregates or fabrics as filter materials to prevent the potential clogging to the pipes and also the drainage layers. For the outlet pipes, they will usually be placed in the trench and backfilled with the native soils. Also, some filter criteria applied for the pipe in the drainage system. For the slotted pipes, the condition here should be satisfied. The grain size with 85% passing for the filter material over the slot width should be higher than 1.2. While for the pipe with circular holes, the DAD of filter materials over the hole diameter should be higher than 1.0. For open joint pipes, we want the DAD over the maximum of opening of the pipe be larger than 2. So these three criteria will be applied for different types of the pipes in the drainage design. The next content we will discuss in this lecture is the design procedure for the drainage system. The figure here shows one example about the drainage system applied for a two-lane highway with an asphalt shoulder. In this example, we see that the thickness of the concrete pavement is 9 inches, and we apply an open graded subbase as the drainage layer. The thickness of the drainage layer is around 6 inches, and this drainage layer is directly connected to an perforated or slotted collector pipe, so that we can lower the water table and remove the inflow. And this is one typical example about the drainage system applied for a pavement structure. Next, we're going to see how we can set up these materials for the drainage system. As we know that the purpose of the drainage system is removing the inflow of the water from the pavement structure. So in order to design an appropriate drainage system, we have to make an accurate estimation about the inflow. In general, there are three major sources of inflow: surface infiltration, groundwater seepage, and meltwater from ice lenses. The first one, surface infiltration, is the most important source of the water, and we should always put this one into the consideration for the drainage design. For the groundwater, if possible, we want to introduce the deep longitudinal drain to lower the groundwater so that we can prevent the seepage into the pavement structure. And for the last one, meltwater. It usually occurs at the region with a very low temperature and frost heave effect. Usually the meltwater and the groundwater won't occur at the same time, so we need to put this one in the consideration for the drainage design. The estimation of the surface infiltration is the most important part for the estimation of the inflow. Usually the surface infiltration is determined by the precipitation rate. The equation here shows the way for us to estimate the infiltration rate at one area. So here we use the Qi to represent infiltration rate. Qi equal to IC times NC over WP plus WC over WP times CS plus KP. Here IC is the crack infiltration rate. NC is the number of the longitudinal crashes. WP is the width of the pavement subject to infiltration. WC is the length of the transverse cracks or joints. And CS is the spacing of the transverse cracks or joints. KP is the rate of the infiltration through uncracked pavement surface. Usually it equals to the coefficient of permeability for hot mix asphalt or PCC. The previous equation is very complicated for us to estimate the infiltration rate. We can actually apply some simplification based on the pavement structure. Here we can assume NC, the number of the longitudinal cracks, as n plus 1, and n is the number of the lengths. Also, we can set WC equal to WP, KP equal to 0, and IC, the infiltration rate of the cracks, as 0.1 feet cube per hour per feet. With that, we can define the inflow rate as Q equal to QI times WP. That is 0.1 times n plus 1 plus WP over CS. So here, if we are considering the concrete pavement, CS is the joint spacing. If we are considering the asphalt pavement, then CS is the constant value. Usually we set it as 40 feet or 12.2 meters. Now let's check one example to see how we can estimate the inflow rate for one pavement. Here we are considering a two-lane pavement as shown in the figure here. The width of the pavement is 24 feet, and the joint spacing is set as 15 feet. Here we are considering a PCC pavement. It wants us to find out the amount of the surface infiltration. Now for the solution, we will first try to find out the information provided by this problem. We are actually given the number of the lengths as n equal to 2, the width of the pavement is 24 feet, and the joint spacing is set as 15 feet. And it wants us to find out the inflow rate and infiltration rate. So here for the solution, we can call the equations mentioned previously. For the inflow rate, Q equal to 0.1 times m plus 1 plus WP over CS. That is 0.1 times 2 plus 1 plus WP is 24, CS is 15, which will give the result as 0.46 feet cube per hour per feet. And for QI, it actually equals to Q over WP. That is 0.46 over 24, which is 0.0192 feet cube over per hour per feet square. So that's the way for us to get the solution for this example. We also want to estimate the inflow from the groundwater seepage. In general, the inflow above the drainage layer is set as Q1 and is determined by the equation here. The figure here shows how we calculate the inflow of the groundwater seepage. Basically, in this equation, Q1 is the inflow and K is the permeability of the soil in the cut slope or in the subgrade. Capital H is the initial height of the groundwater table above the impervious layer, and H0 is the vertical distance between the bottom of the drainage layer and the impervious layer. Li is the distance of influence and is usually determined by the equation here, Li equal to 3.8 times H minus H0. With these equations, we are able to find out the inflow rate above the drainage layer. In reality, the groundwater seepage can also enter the pavement structure from the bottom of the drainage layer. In that sense, we also need to estimate the inflow below the drainage layer, which is Q2. Usually, the value of Q2 can be obtained from the figure on the right. In this figure, the horizontal axis represents the value of Li plus 0.5 W over H0. Here W is the width of the road, and the vertical axis represents K times H minus H0 over 2Q2. So we have the value Q2 as shown in the y-axis. In this figure, each line represents the value of W over H0. So the first line here is the result for W over H0 at point 1. We can find out the line with different values of W over H0. By finding the value of Li plus 0.5 W over H0, we are able to find out the value of this term. In that sense, we can calculate the value of Q2. Once we find both Q1 and Q2, then the lateral flow from the groundwater seepage can be estimated as QL, which is Q1 plus Q2. Moreover, we can find out the groundwater inflow to the drainage layer per unit area as Qg as 2 times Qa over W. Or if the pavement is sloped to one side and the collector pipes are installed only on one side, then the lateral inflow per unit length of the pipe will be QL equal to 2 times Q1 plus Q2, and Qg equal to Q1 plus 2Q2 over W. Now let's see how we can estimate the groundwater inflow in this example. Here we will use the same pavement structure to the previous example, and we assume that the native soil is in a silty sand, and the permeability is set as 0.34 feet per day. That is 1.2 times 10 to the power minus 4 centimeter per second. We want to use all this information to determine the inflow QL and Qg. In this figure, we can see that the pavement is a sloped pavement with only one pipe. Also, we are given the height of the initial groundwater table and also the vertical distance from the drainage layer to the impervious boundary. We are also given the value of WP, and we can use all this information to find out the value of QL and Qg. From the example, we know that the pavement is sloped and the collector pipe are only installed on one side of the pavement. So we need to call the following two equations to estimate the QL and Qg. First, QL in this case is set as 2 times Q1 plus Q2, and Qg is Q1 plus 2 times Q2 over W. In this problem, we want to find out Q1 and Q2 in order to get the values of QL and Qg. So in the solution, we will first try to get the value of Q1. From the figure, we can see that H is 25 feet, H0 is 20 feet. Then we can estimate the value of Li, which is 3.8 times H minus H0, that is 3.8 times 25 minus 20, which will give you the value as 19 feet. And then we can call the equation for Q1 to find out the value of Q1. Q1 equal to K times H minus H0 square over 2 Li. Here we know that K is the permeability of the native soil. So K is 0.34. That one give us the value as 0.34 times 25 minus 20 square over 2 times 19, and the result is 0.22 feet cube per day per feet. So that's Q1. Now for the estimation of Q2. For the value of Q2, we need to pick the value from the figure that we mentioned previously. In order to find out the value, we need to determine which line we're going to use and also the variables for the horizontal and vertical axis. For the horizontal axis, the variable is Li plus 0.5W over H0. In this example, we know that Li is 19 and W is 24. H0 is 20, which will give us the value as 2.05. In addition, we need to determine which line it is. That is W over H0. So we have W as 24, H0 is 20, which is 2.2. And now by using these two values, we use this one to find out which line we're going to use, and we use this one to find out the which point in the line we should choose. So with these two values, we can get the value of the y-axis as K times H minus H0 over 2Q2 equal to 0.74. This is the value here is read from the figure, and this one is equivalent to Q2 equal to K times H minus H0 over 2 times 0.74. Here we have K is 0.34 times H is 25, H0 is 20, and that will give us the result as 1.15 feet cube per day per feet. Finally, we can find out the values of the QL and the QG. First, for QL, it equals to 2 times Q1 plus Q2. That is 2 times 0.22 plus 1.15, which will give us the result as 2.74 feet cube per day per feet. And for QG, that is Q1 plus 2Q2 over W, which is 0.22 plus 2 times 1.15 over the width is 24. So that one give us the result as 0.057 feet cube per day per feet square. This is actually applied to the same pavement structure. And from the previous example, we see that the inflow from the surface infiltration Qi equals to 0.46, which is much larger than Qg here. So usually for the groundwater seepage, we can actually ignore that impact. So that's all about the lecture today. Thank you very much for your attention. In the next lecture, we will try to finish all the rest contents in drainage design.